welcome to part 3 in the bonding series. We're going to continue talking about Lewis structures. We did Lewis dot diagrams at the end of the last video, and those will lead into what we call Lewis structures, which are also called Lewis dot diagrams, and they show how the valence electrons are actually arranged in the atoms that are in a molecule. So in the last video we showed how they're arranged on just a single atom, but now we're going to start talking about how they're arranged when those atoms bond with another atom. It gives us an idea of the connectivity of a molecule, which is how those atoms are actually attached to each other. There are multiple different ways of representing this, as I've shown here, and each of them has their own name. So this is called a structural formula because it shows the actual structure of the molecule. In other words, how things are attached to each other. This is called the ball and stick method, and it gives us some idea of the 3D geometry of the molecule, how they sit in 3D space. So this is the perspective drawing, which looks very similar to the ball and stick, except everything is still done with lines. A dark wedge indicates that something is moving out towards you in 3D space, and a dashed wedge indicates that something is moving away from you in 3D space. It's a simple way for us to be able to draw a shape that looks like the ball and stick model without having to be like crazy awesome artists to do it. Then we have a space filling model, and this is more closely representative of what it would look like in real life. If we had an atomic level microscope that we could look at an actual molecule, it would look more like this. Molecules don't actually have these long bonds between the atoms sticking out like actual sticks. All of the electron clouds kind of overlap each other, and the bond is in this region where they overlap. So this just kind of gives us an idea of how it might look if we could see it on that atomic level. Okay, so here's how you get from dot diagrams to Lewis structures. Remember, dot diagrams are the individual atom, and Lewis structure is where we're talking about those atoms being involved in a molecule. Alright, so let's revisit here. We've got a hydrogen that's got 1 valence electron, and then oxygen had 6 valence electrons. Okay? So if we were to take both of these things and we want to start connecting them with each other, then what we're going to try and do is make pairs of electrons. So this single electron on the hydrogen wants to pair up with another one. This oxygen right here has 2 spots where that can occur. So one of the electrons from oxygen and one of the electrons from hydrogen are going to partner up. Like I said, there's 2 places for that to happen, so the oxygen can bond with 2 hydrogens. A bond is represented by a single line, and that single line is made up of 2 electrons. One of them came from one element and one of them came from another element. Okay? Here I'm showing you that line where half of it's colored blue and half of it's colored red, so you can still understand that the electron comes from each of those elements, 1 electron from each. But, you know, in reality we just draw it with a single line, and you need to understand that that line represents 2 electrons, 1 from the hydrogen, 1 from the oxygen, and since they're sharing those electrons, that must be a covalent bond. And since oxygen is way more electronegative than hydrogen is, you need to remember that that is a polar covalent bond. Okay, so let's take a look at this a little bit more with several different examples. We've already done the water example here, so I won't go back into that. We can talk about methane, which is CH4. That means carbon is bonded with 4 hydrogens. So let's look at the Lewis dot structures, or the dot diagrams for carbon and hydrogen first. Alright, carbon has 4 valence electrons. Alright, and hydrogen has 1 valence electron. Remember that these lone pair electrons want to partner up. That means that carbon has 4 spots open to bond with hydrogen. So that means 4 hydrogens bond with it. This is a Lewis structure. It indicates bonds, it indicates elements, and it indicates lone pair electrons. So those are the things that every Lewis structure will have or could have. Not every Lewis structure will have lone pair electrons. As you can see, this one doesn't. But if they're supposed to be there, you have to put them there in order for it to be an actual Lewis structure. Okay? So let's look at how we would write that, building it. Okay? We would put our carbon in the middle, and we would put its 4 electrons around it. Okay? Then we would put a hydrogen next to each of those with its electron. And just like in the other picture, we would then connect those because every bond is made up of 2 electrons. Alright, and then this is just a preliminary. You don't have to do that every time, just in the beginning until you maybe get used to it. Then you can turn that into just a single line to represent your bond. Okay. Methane, incidentally, is an organic molecule. I don't know that I've mentioned this in the video series, but in class we've talked about what organic means, so I'll put it here as well. Anything that's organic is something that contains carbon, except for CO2. For whatever reason, CO2 is not considered to be an organic molecule, even though it has carbon in it. So there you go. Ammonia, NH3. Here's the Lewis dot diagram of that, where they've taken nitrogen, which has 5 valence electrons. So it looks like this. And then we've got our hydrogen with 1 electron. Now we already have a lone pair here, so that's not going to want to do anything. It's already partnered up. But there are 3 spots open for a partnership, and so that's why 3 hydrogens bond here. And remember, every 2 electrons is a bond. So this is what the Lewis structure ends up looking like for ammonia. Okay, then we have carbon tetrachloride. Alright, that means a carbon surrounded by 4 chlorines. Again, carbon has 4 valence electrons. That means there's 4 spots open. Chlorine has 7 valence electrons. So it only has 1 spot where it can bond. Every other pair of electrons here is already partnered up. They're good to go. So this carbon has 4 spots open. The chlorine, oops, I missed an L, has 1 spot open. So we're going to surround our carbon here with our chlorines, and let's see if I can color coordinate that for you. So the chlorines I've gone over in red, and the carbon I've gone over in blue, so that you can see that 1 electron comes from the carbon and 1 electron comes from the chlorine. Okay, so then we're going to take each of those shared electrons there and turn it into a single line. Okay, and that indicates a bond between carbon and chlorine. Now we normally don't do these lines here for just regular lone pair electrons, but we can, and that will give us what we call an alternate Lewis structure. Since 2 electrons can be represented by a line, then you will sometimes see that happen where instead of doing all of these dots around the elements and making it kind of look cluttered like that, you'll just see these 3 lines. That's 2 electrons, that's 2 electrons, and that's 2 electrons. And that's perfectly fine. You can do that. You generally only see that happen, you only do the lines if the atom is surrounded on all sides by electrons. Here where we have the nitrogen, you really would not see them do a structure that looked like this there for an alternate Lewis structure. That you would not see that. Okay, so don't do that. Only use these lines if you're surrounded on all sides by electrons. Okay, so let's figure out how we draw an actual Lewis structure, and this is going to be for molecules that do not contain charged atoms. So we'll get to ones that do contain charged atoms in a little bit. Alright, the first rule. or the first step I should say, is to count the total valence electrons for a molecule. Okay, in order to do this, you're going to find the number of valence electrons for every atom in that molecule and then add them all up. So let's do that. We're going to do the Lewis structure for methane, that's CH4, since we already saw it up above. Carbon had 4 valence electrons, and hydrogen has 1 valence electron, but there are 4 of them. So we're going to multiply 1 valence electron by 4. So 4 times 1 is 4, plus 4 more is 8. So there are 8 valence electrons in methane. Okay, so we did step 1 just then. Step 2 says, draw a skeleton structure with the neediest, which means the least electronegative atom in the center, okay? And the least electronegative atom is the one that needs more electrons, okay? And then you're going to connect that center atom to all the other atoms in the molecule with a single bond. Remember that each bond represents 2 electrons. Remember our periodic trends, electronegativity increases in this direction and in this direction. So we want the least electronegative element to be in the center, which means moving in this direction. Okay? However, there's a little caveat to that. You cannot ever have hydrogen in the center of a molecule. Okay, so we need to put the least electronegative element in the center. Between these 2 elements, that would be hydrogen, but I just told you hydrogen can never be the center element, and so it's going to be carbon. Alright? So the rule here, what we're trying to do for number 2, put the least electronegative atom in the center and then connect all the other atoms to it with a single bond. And I want you to add in here, hydrogen can't be in the center. Okay? So we're going to surround it with hydrogens with a single bond. Okay, so we did step 2. Step 3 says use up all the remaining electrons from the valence electrons we counted in step 1 to add lone pairs to all the atoms in the molecule until either their octets are met or until you run out of electrons. Add electrons to the most electronegative atom first. Okay, well we need to see how many electrons we used up. Remember, every bond is equal to 2 electrons, so we used 2, 4, 6, 8. We used up 8 electrons, which means we have 0 electrons left to play with. So right here where it says use up remaining electrons, we don't have any remaining electrons. We used all of ours, so step 3 is done. Step 4 says make sure all atoms' octets are met, and if they aren't, shift electrons around to create bonds until the octet rule is satisfied for every atom. The exception is hydrogen, which only wants 2 electrons, and sulfur, which could get up to 10. Okay? Remember, an octet is referring to the idea that every atom wants to have 8 electrons in their valence energy level. Okay? So let's see. Carbon right now has 2, 4, 6, 8 electrons around it. So carbon's octet is met. It's happy. Hydrogen doesn't want 8. It wants 2. Okay? Now remember, these are covalent bonds. They're sharing those electrons. So carbon gets to feel like it has all of these electrons, and hydrogen gets to feel like it has all of these electrons. So every hydrogen has 2 electrons around it. Okay? So this molecule is happy. The octet rule has been met. Okay, last step. If there are extra electrons after all the octets are met, then you're going to place them on the center atom. We didn't have any extra electrons at all, so that means that this is the final Lewis structure for methane. And we know that to be true because that's the same structure that we saw earlier in this video. Okay, let's do another example. Let's do carbon dioxide this time. Alright, so we've got CO2. Okay, the very first step was to count up your valence electrons. Okay, there are 4 valence electrons in carbon, and there are 6 in oxygen, and we have 2 oxygens. Okay, so 6 times 2 is 12, plus 4 more is 16 electrons. Okay, then step 2 says to put the least electronegative element in the center. Now here's a helpful hint. 9 times out of 10, like in most situations you run into, the first element in the molecule is going to be the center element. So if you're like ever in doubt, roll with that, okay? So usually the first element goes in the center, and you also know hydrogen can never be in the center. And as it turns out, if you look at the periodic table, carbon is less electronegative than oxygen is because it's further this way on the periodic table. So it does belong in the center. Alright, so we're going to put carbon in the center, and then you surround it with the other atoms in the molecule with a single bond between each. Okay? Then we're going to subtract how many electrons we just used up. So we have 2 here and 2 here. So we just used up 4 electrons. So we have 12 electrons left to play with. So we have to take those 12 electrons and put it around our molecule. But we start by putting it on the more electronegative element. Oxygen is more electronegative than carbon is, so we're going to start putting electrons on the oxygens. So we got 1, 2, 3. Notice how I'm not partnering them up yet. I did 1 on each side of oxygen first, and then I'll come back around and give it a partner. So we got 1, 2, 3, 4, 5, 6. Now this oxygen, 7, 8, 9, 10, 11, 12. Okay, so we just used up our 12 electrons, and we have no more left over. Okay? Alright, so that was step 3, just if you're following along here. We used up all the remaining electrons until we ran out of electrons, and we did it by adding electrons to the most electronegative atoms first. Okay? Now we have to go back through and make sure that all the atoms' octets are met, and if they aren't, we're going to shift those electrons around to create new bonds so that the octet rule is satisfied. Okay, so let's check the oxygen. We've got 2, 4, 6, 8. There are 8 electrons around this oxygen. And now here's a shortcut. This oxygen looks just like this oxygen, which means they have to be identical. So that means this also has 8 electrons around it. Now let's check carbon. Okay, carbon has 2, 4 electrons around it, which means the octet rule is not met for carbon. So we need to create some new bonds. So we're going to shift a pair of electrons from this oxygen into a new bond right here, and then we'll redraw the molecule. So we've got something that looks like this now. Let me darken up those electrons. Okay, so right now we've got 2, 4, 6 electrons around carbon. We've got 2, 4, 6, 8 electrons around this oxygen. We've got 2, 4, 6, 8 electrons around that oxygen. So the oxygens are still both good, but carbon doesn't have an octet yet. It still only has 6 electrons. So we're going to take another pair of electrons from over here and shift them into a bond and redraw the molecule. Okay, so we end up with something that looks like this. Alright, now let's check the octet rule again. We've got 2, 4, 6, 8 for that oxygen, 2, 4, 6, 8 for that oxygen, and 2, 4, 6, 8 for the carbon. That means all of the octet rules are obeyed for every element. There are no extra electrons after the octets are met, so that means that this is our final structure for carbon dioxide. Okay? Alright, let's do another one. Let's do beryllium difluoride. Okay, so how many valence electrons does beryllium have? 2. And then fluorine, being a halogen in the 7th group, has 7, but there are 2 of them. Okay, so we have 14 electrons here, and 2 more gives us 16 electrons. Okay, now we need to put the least electronegative element in the center. Okay, beryllium is further to the left than fluorine is. In fact, fluorine is the most electronegative element on the whole periodic table, so it's definitely not going to be the center. So beryllium is going to be the center, and we surround it with all the rest of the elements attached with a single bond. Now we're going to subtract the amount of electrons we just used. So we've got 2 here and 2 here. So that's 4 electrons that we just used up, which means we have 12 left. We're going to put those 12 electrons on the most electronegative elements. So that's going to be fluorine. So we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, now you may be wondering, because I haven't mentioned it yet, why did I stop when I got to 6 here? Why didn't I just keep going? How did I know not to put all 12 electrons here? Well, it's that octet rule again. Okay, remember, every element wants to have 8 electrons. This fluorine, it already has 2 electrons right here, so the maximum number that I could put around it would be 6, and that gives it its full 8 electrons. So once I got to 6, I needed to move over here and start putting the rest on that one. Okay, so we used up our last 12 electrons, and we don't have any more electrons left. Okay, and now we need to check the octet rule. Okay, so this fluorine has 2, 4, 6, 8, and this one looks just like that one does, so I know it has 8. Beryllium, it has 2, 4. It does not have 8 electrons. But remember, in the previous video we talked about elements that can break the octet rule. Beryllium is one of them. Okay, beryllium only wants 4 valence electrons, which means that this is the final Lewis structure. That's the correct answer. Alright, one more practice one. Let's do sulfur hexaiodide. Okay, so how many valence electrons does sulfur have? 6. And how many valence electrons does iodine have? 7. But there are 6 iodines total. So 6 times 7 is 42, plus 6 more is 48 electrons. Okay, then we need the the least electronegative element in the center, and that would be sulfur, because it's further to the left than iodine is. You surround that sulfur with all the rest of the atoms in the molecule attached by a single bond. So let's see. Iodine, 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 and iodine, iodine, iodine. Okay, so I'm attaching them all with a single bond. Okay, now we figure out how many electrons we just used up. Remember, every line equals 2. So we've got 2, 4, 6, 8, 10, 12. So we just used up 12 electrons. So we have 36 electrons left, and they get placed on the most electronegative element first, which is iodine. So we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36. Okay, so we've got 36 electrons now that we've used up. And so we have 0 electrons left. Alright, now we go check the octet rule. So iodine has 2, 4, 6, 8. This iodine looks like all of the other iodines, so I know that all the rest of them have 8 electrons. That's good. Their octet rule has been met. Let's check sulfur. 2, 4, 6, 8, 10, 12. Sulfur has 12 electrons. Sulfur is one of the elements that can break the octet rule. So this is the correct structure for sulfur hexafluoride. Okay, let's talk about how to draw Lewis structures if we do have charged atoms in the molecule. Okay, it's exactly the same as what we've done before, except when we go to count the valence electrons, if the molecule has a negative charge, it's an anion, then we're going to add electrons to it. If it's a cation, meaning it has positive charge, we're going to subtract electrons from it. Okay, and the reason for that is since we're counting up electrons, if it's got negative charge, that means it's got extra electrons, so we need to add those in. If it's got a positive charge, that means it's lost electrons, so we need to take those out. Then we're going to repeat the steps 2 through 5 from above, and then the very last step is going to be to find the charge on each atom. We'll do that in just a second. Okay, so let's do SF5 minus 1. Okay, alright, so we're going to count up all of the valence electrons just like normal. So sulfur has 6, okay, fluorine has 7, but there are 5 of them. And then we have this minus 1 charge. That means we have 1 extra electron, so we're going to add that extra electron in. Okay, so 5 times 7 is 35, plus we've got 6 and 1 more makes 7, so we've got 42 electrons. Okay, now we put the least electronegative element in the center, which is going to be sulfur, and we surround it by all the rest of the elements in the molecule attached by a single bond. Okay, then we count up how many electrons we just used. 2, 4, 6, 8, 10. Okay, now we're going to place those 32 electrons that we have left on the most electronegative element first, which would be the fluorine. Okay, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30. So we just used up the 30 electrons, which means we have 2 left. And if we have any extra electrons, they are always placed on the center atom. So we'll put 2 extra electrons right here on the sulfur. Okay, now we're going to check to see that the octet is met. So we've got 2, 4, 6, 8 for that fluorine. All the other fluorines look like this one, so they have 8. And sulfur has 2, 4, 6, 8, 10, 12 electrons. Okay, so we moved through all the steps that we know how to do so far. And now we're at this step 6 where we need to find the charge on each atom. Okay? That's called finding the formal charge. Alright, there are 2 ways to do it, and I'm going to show you how to do each of them. Okay? The first one is what I call by inspection. Alright? We look at everything based on the number of valence electrons that an element has. Okay, so here's an example. Here we've got methane. Hydrogen is supposed to have 1 valence electron, and carbon is supposed to have 4 valence electrons. Alright, so what we're going to do is look at the bonds between those atoms, and we're going to go back to thinking about those bonds as one element contributed 1 electron and the other element contributed the other electron, and we're going to say that those elements own those electrons, and those are the only ones that we care about. Okay, so right now hydrogen has that 1 valence electron that belongs to it. Okay, so it's got the exact same number of electrons as it's supposed to have as far as its valence electrons go. And carbon has 1, 2, 3, 4, and carbon is supposed to have 4 valence electrons. That means that there is no charge on either of these elements. They do not have more or less valence electrons than they're supposed to have. Okay. Alright, let's look over here at this molecule for an example. Oxygen is supposed to have 6 valence electrons, and sulfur is supposed to have 6 valence electrons. So sulfur has 1, 2, 3, 4, 5, 6 electrons right now. It has the number that it's supposed to have. That means there's no charge on sulfur. It doesn't have any more or less electrons than it's supposed to. Okay, let's take a look at this oxygen. It's got 1, 2, 3, 4, 5, 6, and it's got 1 out of this bond here. That makes 7. Okay? Oxygen is supposed to have 6 valence electrons. This one has 7 valence electrons right now. That means that it's got 1 more electron than it's supposed to have. So this oxygen has a -1 formal charge. This oxygen looks exactly like this oxygen does. So it's going to have a -1 formal charge for the same reason. Okay, let's look at this oxygen. We have 1, 2, 3, 4, and then we get 1 electron from each of those double bonds there. So that makes 5, 6. So it has 6 valence electrons, and it's supposed to have 6 valence electrons. That means there's no charge on this oxygen because it doesn't have any more or less electrons than it's supposed to have. The second method to calculating formal charge is to use an actual formula. Here's the formula. Formal charge is equal to the number of valence electrons for the element that you're figuring the formal charge of minus the number of lone pair electrons around that element minus the number of electrons participating in a bond from that element divided by 2. So let's go back to this one. We'll talk about hydrogen first, okay? So the number of valence electrons that hydrogen has is 1 minus the number of lone pair electrons currently around this atom. There are no lone pair electrons around that hydrogen, so we put 0. Minus the number of electrons participating in a bond divided by 2. Okay, here's a bond. There are 2 electrons in that bond, so we're going to put 2, and then we have to divide that number by 2. Okay, so 2 divided by 2 is 1, so we have 1 minus 0 minus 1. That gives us a 0 formal charge for hydrogen. And these 3 hydrogens look just like that one, so they're all going to have 0 formal charge. Okay, let's look at carbon. The number of valence electrons is 4. There are no lone pairs around that carbon right now. And there are 8 electrons participating in a bond right now. So we've got 2, 4, 6, 8. And then we divide that number by 2. So 8 divided by 2 is 4. You have 4 minus 0 minus 4 gives you 0. So exactly what we got when we did the inspection method. Okay, the same thing is true for this molecule, sulfur. We've got 6 valence electrons around sulfur, that's this number. The number of lone pair electrons currently around the atom, that's 2 right there. And then the number of electrons participating in a bond, 2, 4, 6, 8. So I just noticed that is wrong. That's supposed to be an 8 right there. You can fix that in your notes. Okay, so we've got 8 divided by 2 is 4. So we have 6 minus 2, which is 4, minus 4 more gives you 0. So we have a 0 formal charge for sulfur, just like we predicted with the inspection method. Okay, now for the left oxygen, that's this one right here. The number of valence electrons that oxygen has, it's always 6, minus the number of lone pair electrons currently around that oxygen. That's 2, 4, 6. Okay? Minus the number of electrons participating in a bond divided by 2. So we have 2 electrons participating in a bond, so we put 2 and then we divide that by 2. So 6 minus 6 is 0 minus 2 divided by 2 is 1. So we have -1. So we have a -1 formal charge on that oxygen, just like we predicted with the inspection method. This oxygen looks just like that one, so it's going to have a -1 formal charge. Alright, let's do the bottom oxygen here. Number of valence electrons, 6. Number of lone pair electrons around it, we've got 2, 4. And then the number of electrons participating in a bond are 2, 4. And then we divide that number by 2. So 4 divided by 2 is 2. So we have 6 minus 4 is 2, minus 2 more is 0. So there's a 0 formal charge here. Okay? So let's do the same thing for our molecule here. I'm going to redraw this to kind of clean it up so it doesn't look so sloppy. Alright, let's get the formal charge for each element. We'll start with sulfur first. Sulfur is supposed to have 6 valence electrons when we look at the periodic table. Okay, so let's, I like to do it by inspection. If you prefer the using the formula, then that's fine, you can do that. I don't care which method you use, just so long as you can find the formal charge. Alright, so what I do is I say that 1 electron from each of these bonds here belongs to sulfur. Okay? Alright, so sulfur has 1, 2, 3, 4, 5, 6, 7 valence electrons around it right now, and it's only supposed to have 6 valence electrons according to the periodic table. That means it's got 1 more electron than it's supposed to have. Electrons are negative, and it's got 1 extra. That means that sulfur has a -1 charge right now. Okay, let's check the fluorine. I say that 1 electron out of that bond belongs to fluorine. Okay, and then I'll go around and count up the electrons that fluorine has. Fluorine is supposed to have 7 valence electrons according to the periodic table. So right now it's got 1, 2, 3, 4, 5, 6, 7. So it has no more or less electrons than what it's supposed to have, which means that fluorine has a 0 formal charge. And these fluorines look exactly like that fluorine does. And when I say they look the same, what I mean is that they each have a single bond and they each have 6 lone pair electrons around them. That means that these fluorines have 0 formal charge as well. Okay? Okay, so the last step here is once we found the formal charge of all of the individual atoms, you add up all of their formal charges so that we can get the overall charge of the molecule. Then you're going to place these brackets around the whole molecule or ion, and since it's a charged molecule, that means it's an ion, and we're going to place that charge in the top right hand corner of those brackets. Okay, so I'm going to put these brackets around my molecule, and then I'm going to add up my total charge. So I've got a -1 and I've got 5 zeros here. So my overall charge is -1, and you put that in the top right hand corner. This overall charge here is the same as we were given at the beginning when they told us this molecule. There it is right there. Okay? So that's how we get the Lewis structure of a charged molecule. Alright, now there will be certain situations in which you could come up with multiple Lewis structures, and so you need to be able to pick the perfect one, the very best Lewis structure. Because on a test, I might say, draw the Lewis structure for such and such molecule. And if there are 4 possible Lewis structures, how would I know which one you were going to draw so that I can give you points? So I will write the question as, draw the best Lewis structure for such and such molecule, and then you'll need to be able to pick the very best one. So here's how you do it. There are 3 steps. They go in order of importance. So the first one is the most important. Every atom has to have their octet met. Okay? If you draw a structure where the octet rule is not obeyed, then you have not drawn the very best structure. Okay? Every element needs to obey the octet rule. Step 2. The structure with the least amount of formal charge is better. Okay? So if you can draw a structure where only a single element has like a -1 charge or something, that's better than having a molecule where you've got, you know, a +1 charge on one element and a +1 charge on another element, and a -1 charge on a different element. Okay, so you don't want the charge to be spread out. You want to have as least amount of charge as possible. Step 3. If the structure has to have formal charge, then the negative formal charge needs to be on the more electronegative elements. Okay, so for example, you would want a -1 charge or something to be on an oxygen rather than being on a carbon, because oxygen is more electronegative than carbon is. So you want the negative formal charge to be on the more electronegative element. Okay? Okay, let's see if we can practice that a little bit. Alright, here we have two different Lewis structures for the same molecule. Alright, in this Lewis structure on the left hand side, we have a double bond to oxygen here, a lone pair on nitrogen, and two lone pairs on this oxygen. So let's look at this oxygen. It's got 2, 4, 6, 8, so the octet rule is obeyed. This one has 2, 4, 6, 8, so the octet rule is obeyed. Let's look over here. 2, 4, 6, 8, and 2, 4, 6, 8. So the octet rule is met on both of those. So we would move to step 2. Step 2 says the structure with the least amount of formal charge is better. Okay, over here we have two elements with formal charge on them. Over here we have 0 elements with formal charge on them. That automatically means this should be the better Lewis structure. So if we were on a test and I asked you to draw the Lewis structure for this molecule, which I probably wouldn't because I think it's a little bit too big for you guys at this point, this would be the Lewis structure that I would expect you to draw. This one is not the very best one. Okay, here's an example of some more polyatomic ions that we might have you draw. I just used a new word, polyatomic ion. Poly means many, atomic is atom, and ion is a charged particle. That means we're going to have a many atomed molecule that has a charge on it. So this right here is a polyatomic ion. It's the ammonium ion. And notice it's in its brackets and it's got its +1 charge. Let's try and find the formal charge on each of the elements real quick, okay? Hydrogen's got 1 valence electron and it's only supposed to have 1, so there's 0 formal charge on each of the hydrogens. Nitrogen's supposed to have 5 and it's got 1, 2, 3, 4. That means it's got 1 less than what it's supposed to have, so there's a +1 charge on nitrogen. That means that the overall charge of this molecule is because of nitrogen. Okay? See if you can go through and figure out what the charge on each of these other elements are. Okay, so hopefully you came up with what I came up with for each of those molecules. Check yourself. Alright, that wraps it up for this video. Thank you for learning with me, and I will see you next time.